VLSos here. This is a video lesson on intersection as a solution. We've talked about what a solution is in a previous lesson. A solution is a value or values that make a relation true. And in this case, we're going to have not just one equation, but two. The first, y is equal to x squared. And the second equation, y is equal to x plus 2. This is a system because I'm considering two equations at once. I want to find a solution to this system, which means finding a value for x and y that makes both of these equations true at the same time. And further, this lesson is going to show that I can find those values as intersections. Intersections on the graph where these equations cross each other. So if I'm going to find solutions as intersections, then I'm going to need to graph these two equations. I could use a graphing calculator. I could use t-tables and calculate and plot some points. Or I might be familiar with these two relatively simple equations and draw them straight away from the familiarity of the mathematics. The first one is quadratic, so its graph is going to be a parabola. If you don't know what the simplest x squared parabola looks like, that's okay. You can put some points in or some values for x. If I substitute 0 in for x, then y will be 0. If I substitute 1 in for x, y is going to be 1. When x is 2, y is 4. This parabola is going to be symmetrical. I could substitute -1 in and -2 in and get these values. And the entire graph of the parabola will connect these points with a parabolic curve. This equation here, the second one in the system, is a line. The line has a slope of 1 because 1 is multiplying the variable x. This is in slope-intercept form, in which the y-intercept is 2. We needn't be familiar with slope-intercept form to do that. That's just a quick way, using previous knowledge, to graph this. We could use a t-table, we could choose values of x and plot it slowly, the most reliable way. This is a y-intercept of 2 and a line that has a slope of 1. There's a single graph that has both equations graphed on it. The intersections are the places where the graphs cross. They cross here and they cross there. Those are the solutions to this system. More precisely, the x and y values of the coordinates of these points of intersection are the solutions to this system. They're the numbers that you can substitute in for x and y that make both equations true at the same time. Where are these coordinates? Well, this is a relatively simple graph in which every square is a unit of 1. And the intersections line up on nice, reliable integer values. The coordinates of this point is 2, 4, and the coordinates of this point is -1, 1. So the solutions to this system, there are 2, and each solution has two numbers, both an x and a y value. The coordinates of those points of intersection. Now, if they're solutions, I should be able to substitute the values in and confirm that it makes both those equations true. Let's do that. I'm going to check my work for the first solution. That means that in the first equation I get a y value of 1 when I take the x value, -1, and square it. And at the same time, I should get a y value of 1 if I take the x value, -1, and add 2. Is this true in both cases? Well, in the first equation, 1 is equal to -1 times itself is indeed 1. And in the second equation, 1 is equal to -1 plus 2 is indeed 1. So both of these equations are true at the same time with the same values. I've checked that that is a solution. And I could check that the other one is a solution as well, using the same technique. Now, finding solutions to systems by looking at intersections on a graph is pretty easy to do if you can graph the equations reliably and the graph is easy to observe where those coordinates are. But that's not often the case. These equations here graph very nicely and the intersections had integer coordinates. But again, that's not often the case, and sometimes when you are looking at a graph, it's hard to tell visually where an intersection lies. And you can be led astray by assuming that it is close to an integer value when it is indeed not. So finding solutions to systems by looking at intersections on a graph is unreliable, it's chancy, and it often doesn't work. So we have other more sophisticated algebra techniques to solve systems, including substitution and elimination, which are topics for future lessons.